Hello everyone and welcome back to Advanced Robotics. Today is day 3 of the camp, so we're going to be talking about building the robot, as well as what parts we use. We're going to go over the different types of commercial off-the-shelf or COTS parts and when to use them, give you some visuals for how these parts work, and show some demos and examples of these parts in action on an actual robot, specifically Masquerade's competition robot from last year. Now what exactly are these COT parts? As I mentioned earlier, COTS means commercial off-the-shelf, or prefabricated parts purchased from vendors. Manufacturers build these parts to certain specifications, meaning they're built to be used with each other without much extra tweaking. And as I'm sure you've guessed, custom parts are ones built by a team specifically for their robot from scratch. These can be useful for more experimental or unique designs. Neither of these are necessarily better or correct. It really depends on the team's style and preference as well as what resources they have available to them. Masquerade uses mostly commercial off-the-shelf parts while Maelstrom uses custom ones, and both teams perform very well. The main structure of the robot is usually comprised of 3 main parts. The main foundation that makes up the chassis, usually channel or some variation of it, fasteners such as screws or nuts which hold pieces together, and insiders and brackets which allow for a greater variety of ways for other parts to be mounted. The foundation or chassis of the robot is built mostly out of 3 parts. Channels with hole patterns designed to allow almost any other part to be mounted onto them. Beams which are used for lighter or smaller subsystems. And extrusion, which is mainly used for lifts because of how easily they can be mounted on top of each other. With a view like this, you can really get a better understanding of what we would use each structural portion of the robot for. Like here we have channels on the outer edge which need more durability, they gotta be more robust. We have beams on the inside here for more lightweight stuff like holding wires, as well as for rotating on things like servos. Because they're so skinny, that gives them a much smaller turn radius, which is useful for things like this because they have to be rotating in and out of the game quite a bit. As you can see there, we have the extrusion as well for the lift. With these mounts that I was talking about earlier that allow it to move up and down almost seamlessly. Fasteners are used to attach parts to each other securely. These include screws, which come in 3 main types. Standards, which are 6 32nds of an inch wide. Button heads, which are similar to standards, but have a dome-shaped head as opposed to a flat one. And rev screws. Some rev screws are slightly different from others. However, they're all similar in the fact that they're made especially for rev brand products, such as lifts or servos, which we'll cover later. Now the other main type of fastener just drives me nuts. Get it? Anyways, the first type is the hex nut, which is your standard run-of-the-mill nut with no real modifications. They're pretty easy to screw on by hand, but in the long run they're not incredibly secure. Next we have Kep's nuts, which are like hex nuts, but with a ring of teeth on one end that allow it to latch onto surfaces more securely. Lock nuts have a ring of nylon on one end that the screw is essentially forced through, creating a very, very tight seal. However, this means they're almost impossible to tighten or loosen without some sort of tool. Square nuts are like hex nuts, but they're squares instead of hexagons. Wild stuff, I know. Next we have pattern mounts and pattern brackets, but what's the difference? Well, pattern mounts, also called insiders, are a little bit smaller in diameter than channels or brackets. This is because they're meant to be attached to the inside of these pieces, as another wall or face for other parts to be mounted onto. Brackets are similar in the sense that they attach other parts to each other. However, they're the same width as channels because they attach to the outside, not the inside. Here's an example of each one on the actual robot. Right there we have an insider, that kind of faceplate kind of thing right there. But that is screwed on the inside of the channel. You can see it's pretty close to the edge, but not exactly on the outside. While up here we have a pattern bracket, that kind of L shape right there. That is screwed to the outside, but it's also screwed to the inside of another part. In this case, a phone mount. Motors are used to apply force to parts that need it at a moment's notice, such as wheels or lifts. Motors are attached to the channel using motor mounts, which are screwed in from the bottom and then tightened around the motor using a screw on the side. Power comes in through the black portion on the back, which is then used to turn the gear or gears in the midsection, and in turn those gears rotate the axle on the other end. Gearboxes, which are the parts of the motor that the axle comes out of, come in various different gear ratios, which are expressed as numbers. The higher the number, the slower but more powerful the motor is, and vice versa. So a 20 would be faster but less powerful than a 60. There are 2 main types of axles we use. Hex axles, which have 6 sides, and D-shaft axles, which are mostly round except for one flat part. Hubs are used to connect the axle to whatever it should be turning, using a combination of screws and the axle's physical properties. While the vast majority of hubs need to be screwed into the wheel or other part that needs rotation, they differ when it comes to how they stay tight onto the actual axle. While a hex axle is able to stay secure due to its geometry, a D-shaft would still wiggle around in the hub a little bit, meaning the hub would need a set screw. Set screws are very small screws in the sides of hubs and similar parts that create tension and ensure that no movement is possible. We want the axle to be able to rotate when power is given to it, but we don't want the wheel or other part to be able to move when there's no power. This right here is a view from the bottom of the robot, and as you can see here, the wires come in from our hub, which we'll talk about in a later video, and then come up to the black part of the motor here, which then turns the axle right there. This axle then connects to this pulley, which stretches up to here, where one of the wheels of our mechanism drivetrain is connected by an axle and another hub right there. Speaking of wheels, there are three main types we would use for a drivetrain. First are basic plastic or rubber wheels called stealth wheels. While they're easy to use, they don't give any real benefit to mobility. However, they can be useful for added traction or stability. Omni wheels, in addition to moving forward and backwards, are able to move left and right passively due to a set of rollers around the edge. This allows for improved mobility in the form of a tighter turn radius. Finally, we have mechanism wheels, which are far and away the best choice for mobility. With rollers positioned at a 45-degree angle, they're able to strafe left and right directly. However, this requires a motor for each wheel and advanced programming to reach its maximum potential. While there are other types of wheels, they wouldn't be the optimal choice for a drivetrain. For example, compliance wheels are compressible and made of rubber, which can be good if you want some leeway for things like collecting game pieces, but could cause some issues if you're driving around the field all game. Foam wheels are similar in this regard. If they're rolling around on the field all the time, they're bound to take some damage and lose some of their effectiveness. As you can see here, we have two compliance wheels, not as our drivetrain, but as our intake for collecting actual game pieces. Since they're so compressible, we can collect pieces at much more irregular angles than we would be able to otherwise. As you can see, this block comes in at an almost 45-degree angle, but because they're so compressible, there's tension created, which then corrects its position here. And this means that we're able to spend a lot less time actually lining up the blocks and more time scoring them. Axles don't always have to have wheels on the end. Gears, sprockets, and pulleys are useful for transferring power from point A to point B. But what's the difference? Gears have shallower teeth that interlock directly into those of another gear, while sprockets have longer teeth that are attached to lengths of chain as opposed to each other. While pulleys are like sprockets, they use rubber belts instead of metal chains, which can be smoother and more elastic. Lifts are mechanisms that extend and retract, usually using string, motors, or some other form of tension. A continuous string lift extends or retracts one stage fully before moving on to the next one. A stage would be one level of the lift, or in the case of this diagram, one of the purple bars. On the other hand, a cascading lift extends or retracts all the levels of the lift at the same time. While cascading lifts require more power, and the stringing process is more complex, they are faster than continuous lifts. Stringing the lift is the process of attaching string from a wheel onto rollers of each stage of the lift. When the wheel turns, the string becomes looser on one side and more tense on the other, which extends and retracts the stages as necessary. Scissor lifts use motors instead of string, and extend and retract by pushing the first stage of a group of beams in and out. As the beams get pushed further in towards each other, the entire mechanism straightens, and can gain considerable height in very little time, and the entire lift can be retracted simply by moving the first beam to its original location. While scissor lifts can be very fast, they trade off the stability and accuracy that string lifts provide. As you can see, this lift here has 4 stages, 1, 2, 3, 4, and each of these stages has a roller here with string connected to it. The string is also wrapped around this spool down here, which in turn is connected to this motor. As the motor turns the spool, this string here is pulled. And that extends and retracts this lift as so. Since all the stages are moving simultaneously, this is a cascading lift. If each stage were to move one by one as so, it would be a continuous lift. Servos are like motors in that they rotate other parts. However, they're built to rotate to an exact angle, as opposed to running continuously, although continuous servos do exist. Examples of both a normal servo and a continuous servo are shown. A servo block is a mechanism built around the servo itself to protect it from damage and make it easier to mount other parts onto it, especially larger or more irregular ones that may require screws. And with that, we're going to wrap up day 3 of Advanced Robotics. Next up on day 4, we're going to cover wiring and electronics. Thank you everybody for watching, have a great day, and take care.